All right, today we're learning how to solve exponential equations that do not require logarithms. And logarithms will be a part of our chapter, and we'll learn how to solve equations that will require logarithms, just not today. So first of all, what is an exponential function, or what makes something exponential? Okay, well, particularly it's going to have a variable exponent. So their exponent will be our variable x, and it will have a positive constant base, so not another variable, a positive value that is not equal to 1. Okay, so this is usually the parent function of exponentials because 2 is our first nice integer positive value that is not equal to 1. Okay, so that's an example of an exponential function. We'll look at graphs of those and things later on in the chapter. Okay. So how do we solve some of these things today where my unknown is an exponent? Okay, well, we're going to use the idea, if I gave you this equation, 5 to the x equals 5 to the second power. Well, all things being equal here, what power would I need to raise 5 to make it 5 to the second power? For these to be equal, hopefully we can see that our exponents here, x and 2, have to be equal. 5 squared has to equal 5 squared, right? There's no other number I can plug in there that would make those equal. And so we're going to use this idea that if I have this matching base on each side, 5 to the something equals 5 to the something, those somethings, our exponents, have to be equal. Okay, and that's the idea that we're going to use to solve without logarithms today. So if each side of the equation has a single matching base, so this is called the base of our exponents here, the 5s, so a single matching base, which they did, then their exponents must also be equal. So that allowed us to take x and 2 and set them equal. Sometimes we might have more steps to solve for x, but we didn't need to there. Okay, let's try another example. Now I have 5 to the 3x plus 1 equals 5 to the 2x. But once again, I have one single matching base on each side, and 5 to the something equals 5 to the something. What's got to be true is these somethings, 3x plus 1, has to be equal to 2x. Those exponents have to be equal for these equations, or these expressions to be equal. So now we just need to solve this linear equation. Let's get our x's on one side. Maybe we subtract the 3x here. So we get 1 equals negative 1x. Divide away our negative 1. And we end up getting, when x is negative 1, these two things are equal. By the way, if you did plug that in, 2 times negative 1 would be negative 2. So we get 5 to the negative second power. And if we plug negative 1 in here, we get negative 3 plus 1. Which is also 5 to the negative second power. So just as a reminder, by the way, negative exponents, remember, means we move that to the bottom of our fraction here, or change its place in the fraction. So this is really 1/25 equals 1/25. But when x is negative 1, that is the value that makes these equal. Okay, let's take a look at another example. Uh-oh. So we notice in this case, we don't have matching bases. We've got a base of 5, and we've got a base of 25. And if they're not the same matching bases, you cannot set the exponents equal. But what we can do is go back and rely on properties of exponents. Now 25, hopefully you recognize, is a power of 5. And if I can rewrite these as a power of a smaller number, for instance, 25, we're going to write as 5 squared. That's equivalent to 25. So if I rewrote 25 as 5 squared, we're going to keep the 3x minus 1 outside our parentheses here. And this side stays the same, 5 to the 4x. Now note, you might remember properties of exponents. When you raise a power to a power, you multiply. And in this case, this 2 does need to be distributed. So when we distribute, we're going to get 6x minus 2. So 5 to the 4x equals 5 to the 6x minus 2. And note, now we do have that single matching base again on both sides. And that's allow us to say that this exponent and this exponent have to be equal. 4x has to equal 6x minus 2. Solve by putting our values of x, one on each side, and divide by negative 2. We get when x is 1. So if I plug in 1 there, 4 times 1 would be 5. We get 5 to the 4th power. If I plug in 1 here, we get 3 minus 1, 25 squared. And if you check these, 5 to the 4th is 625. 25 squared is 625. They are equal when x equals 1. So this was just checking our work here to show that, in fact, when x is 1, they are equal. Okay, here's a bunch more examples we're going to do. And there's a few more after this. I know this is a lot. But let's use, again, some of these properties of exponents. Now, first of all, when you see a fraction like this, to bring things out of the denominator, to get rid of the fraction, we're going to go back to negative exponents. If you remember, a negative exponent changes something's place in a fraction. So we're actually going to rewrite this to bring 125 up. We're going to rewrite it as 125 to the negative 1st power. Now I no longer have a fraction, so that's nice. This will be a little easier to work with. Now hopefully you recognize these are both powers of 5. We don't have a matching base, but they are both powers of 5. 25 is 5 squared, which again when we rewrite these we use parentheses. 125 is 5 cubed, 5 times 5 times 5, whoops, to the negative 1st power. Okay, now once again, when you have a power raised to a power, properties of exponents, we multiply. So we get 5 to the 2x equals 5 to the negative 3rd. And now we have a matching base on each side, which will allow us to set the expressions of our exponents equal. 2x has to equal negative 3, which means x equals negative 3 halves. Now, of course, can you check this? Yeah. If I plugged in 25 to the negative 3 halves power. Wow. Let's see if we can figure this out. Well, let's make our exponent positive by moving it to the bottom. Right? That's how we would deal with a negative exponent. And then remember our fraction exponents. The bottom tells us what root we're taking. The second root of 25 cubed. What's the square root of 25? 5. And 5 cubed is 125. It does end up equaling the same value at the right. So there's our answer when x is negative 3 halves. Okay, let's try example 5 here. Now be careful, these are not powers of 8. They're not powers of 4 either. Right? This is 4 squared, but this is not a power of 4. In fact, the only way we can make these bases match, which we can, these are both powers of 2. 8 is 2 to the 3rd power. And 16 is 2 to the 4th power. And now we'll be able to get that matching base. We do need to distribute here. Remember, power raised to a power, we multiply. Distribute if necessary. This gives me 2 to the 4x minus 4 equals 2 to the 3x. And now that we have matching bases, we can set the expressions in our exponents equal. 4x minus 4 has to equal 3x. Put our x's on one side of the equation. Negative 4 equals negative 1x. And dividing by negative 1, we get x equals 4. Okay, you can plug in and check there. 8 to the 4th power and 16 to the 4 minus 1, or 16 cubed. But those do equal each other, believe me. Let's do number 7. What do I do again if I've got a fraction? Let's bring this guy up. Let's make that 9 to the negative 1st power. Okay, so again, if you have something in the denominator of a fraction, bring it up. Give it a negative exponent, negative 1st power. Now up in the top, we do need to distribute. Negative 1 times 3x makes negative 3x. And I note that I think we can rewrite these both as powers of 9. 81 is 9 squared. Now I'm not putting parentheses this time because it didn't have an exponent other than 1 on it. But I do have matching bases, 1 on each side. We can go ahead and set the exponents equal. Negative 3x has to equal 2. So x equals negative 2/3. And you can put the negative in the top, in the bottom, or in front of your fraction, but overall, negative 2/3. All right, last example here. And this one initially looks a lot harder than it is. I mean, it doesn't look as hard as some of the previous examples. But when we try to make our matching bases, this does become a little more difficult to think about until you remember properties of exponents. You might remember anything to the 0 power equals 1. Anything to the 0 power is 1. So that means 1 is kind of like a magical base we can use here. If I wanted to rewrite these both as the same base, you can rewrite 1 as any base you want to the 0 power. Except for 0. 0 to the 0 power is like defined, but we won't go too into that. You can replace 1 as 5 to the 0 power. And now that we have those matching bases, we can set the exponents equal. When does x minus 3 equal 0? When x is positive 3.